Hello everyone, this is Dr. Lennon, and I just wanted to go over a few of the solid figure three-dimensional geometry formulas that we did today. So uh, recall we did some two-dimensional versions where we talked about areas and perimeters. So with three-dimensional, the analogous concepts are surface area, the area around the outside. You could kind of imagine that like the amount of wrapping paper you would need to gift wrap the objects, and volume, which would be the number of 1 by 1 unit cubes that you could fit inside. So if we look at this figure, this is a rectangular box. We could look at two of the notions, both the volume and the surface area. So the volume is the easier two. So the volume of a box is just going to be given by, let's say, basically it's going to be length times width times height. So those are just the three dimensions. So for this particular box, the volume is just given by, if we consider the length and the width to two dimensions, on the floor, we would have 5 times 11, and then the height would be 7. So when you multiply those three together, you get, let's see, 5 times 11 times 7, that comes out to 385. And the units, when you have volume, like I said, since they're the amount of like little 1 by 1 cubes you could fit on the inside, they would be inches cubed. I prefer to write it with inch with a little superscript of 3, but you may also sometimes say C385 and then CU period, IN period. So both would be equivalent. If we spoke about the surface area, so the surface area for this one would be the amount of the area kind of on the top, bottom, front, back, and left and right. Anytime you have a rectangular box, there's 6 faces, and each pair of faces is going to have a similar area. So here the surface area, we would have 2 times 7 times 5. That would be the front and the back. And then we would have 2 times, let's say, the top and the bottom, and those dimensions are 5 and 11. And then you would have the third pair, which is the left side of the box and the right side of the box. So that would be 2 times 7 times 11. So you could add all of those up, and let's see what we get. We get 334, and this is going to be square inches. So again, I prefer to write it like this, but you may also see it as 334 SQ period, IN period. So both of those are going to be equivalent. Okay, so let's go ahead and move on to the next example. So the next example is if we have a cylinder. So let's say example, let's determine the volume and we'll say the lateral surface area of a cylinder with radius let's say 3.5 meters. That is 10 meters long. So a cylinder basically is just a circular object that goes up and down like this. You think of like a pipe, and the radius would be maybe this dimension here. That would be our radius, and then our height would be this one here. So the easiest way to think about the volume is you could kind of think about like stacking pancakes up that are each 1 unit thick until you get to the top. So your typical volume formula here for a cylinder is going to be the area of the circle that's 1 unit thick, so that would be pi r squared times the height of the object. So in this example, the radius is 3.5 meters, so we would have pi times 3.5 squared times our height of 10. And again, pi you can approximate by about 3.14, but really your precision depends on how much accuracy you need. Remember that number goes on its decimal expansion forever and ever with no discernible pattern. So let's say we just round it 2 decimal places. This would come out to about 384.85, and now we would have meters cubed. Those are the dimensions here. Now, for this example, we talked about the lateral surface area as opposed to the total surface area. Now, if it were a pipe, usually the top and the bottom are going to be open. They're not going to have, say, lids on them. But if we talked about maybe like a can of Pringles, you're going to have a closed top and a closed bottom. So if we talk about the lateral surface area, basically you're not including the top and the bottom as part of the surface area. Whereas if you talked about the total surface area, you would. So the top and the bottom would just amount to adding 2 circles. So you'd basically be adding 2 pi r squared to your lateral surface area formula. But what is the lateral surface area? Well, if we want to think about the lateral surface area, if you took a cylinder like this and imagine you snipped it and you cut with a pair of scissors that dotted line all the way through and you unwrapped it, what you would end up with is you would end up with a rectangle. And that rectangle, it would have the same height as your cylinder, but the interesting thing is if you looked at the width of this thing or the base of this thing, it would have exactly the base that is the same length as the circle, the circumference of the circle that creates that cylinder. So the base here would be 2 pi rh, which is our circumference formula. So a lot of these 3-dimensional formulas are determined, or they come from our 2-dimensional formulas that we learned. So the lateral surface area here would be, sorry, I included the h and the base. The base should just be 2 pi r. So the base is 2 pi r, and this vertical side of the rectangle that we're created is h. So our lateral surface area formula is 2 pi rh. So we can just plug in our numbers and we will get exactly that value. So we get 2 pi, we had a radius of 3.5 and a height of 10. So what do we get there? We get 219.91, and that is meters squared. All right, so what about the next example? Let's go ahead and talk about a cone. So in this next example, we want to find the volume of the cone. So the cone looks like it's going to have a similar formula for the volume as the cylinder. So the things that are going to be important are the height here, which is 12, and the radius of the base, which is 5. 13 is what is known as the slant height, and that does come up, but it comes up if you look at the surface area formula, which we won't be talking about too much. So what is the volume formula? Well, the volume formula here of a cone is exactly the same as the volume formula for the cylinder, but we just multiply by 1/3. So we get 1/3 pi r squared h. So the volume for this example is just going to be 1/3 pi. The radius is given to be 5, so 5 squared. And then we use 12, which is the height. We don't use 13, which is known as the slant height, the slight of one of those edges. And then we can go ahead and plug that in. And again, that's going to be cubic feet in this example. So that comes out to 314.16. And again, that's going to be feet cubed here. Lastly, let's just talk about one more formula that comes up, and that is the surface area and the volume of a sphere. Again, you may forget some of these formulas, but just know that they're out there and you can look them up. That's the most important thing, and you just have to identify the proper things. A lot of times you might see them give you the diameter instead of the radius, and you just want to divide by 2 then. So let's say, example, find the volume and surface area of a sphere with radius 8.3 centimeters. So here's the two formulas. The volume, so a sphere again is just basically the shape of a perfect ball. So it's the three-dimensional analog to a circle. So if we call that the radius, the two formulas, the volume of a sphere is given by 4/3 pi r cubed, and the surface area is given by 4 pi r squared. So again, we just need to plug the radius into each of these formulas, and we will have the answers required. So not too much math here, really just plugging things in and applying them to the calculator. So let's go ahead and see what we get here. So we get a pretty large number, 2,395.10 centimeters cubed for the volume. And for the surface area, we're going to get 4 times pi times 8.3 quantity squared. So let's see what this comes out to. So this one comes out to 865.70. And that's basically it for the solid figures that we'll encounter in the section. Like I said, if you forget some of the formulas, they're available on a quick Google search, and you just need to make sure you're plugging everything appropriate and typing it into the calculator all right. And a lot of times you can see how these things relate to some of the formulas that we've seen from either rectangles, circles, or triangles in the two-dimensional case. So this is Dr. Lennon signing off.